d rotations. So what we've done so far in 2D is we've considered rotation about the z-axis. So remember, this was our x0, y0 frame, and then we rotated the frame about the z-axis. We ended up with x1, y1, and I'm just going to assume that this angle is psi. And we wrote the corresponding rotation matrix R1 with respect to 0 as cos psi minus sin psi, sin psi, cosine. Okay, but in reality, this is not 2D. It's actually, you can think of this as 3D. If you look at this from the z-axis, so I'm going to redraw the same figure, but now show it in 3 dimensions. This is our x, y, and then z0, which is I had not shown, is pointing out of the plane. This angle here is psi, and then this is y1. And because it's rotation about z-axis, the z-axis itself will not change. So z0 and z1 would be in the same direction. Now, when we talk about 3D, we would have a 3-dimension 3x3 rotation matrix, not a 2x2 matrix. So you can represent this rotation matrix. We'll call that rotation about z, parameterized by the angle psi, to be cosine psi minus sin psi, sin psi, cosine psi. And then there'll be 0, 0, 1 on the last row. That 0, 0, 1 indicates that when this rotation matrix is multiplied by a vector, it will lead to no changes for a vector which is in the z on the z-axis. So the z vector will not change, which is what we expect. The rotation about the z-axis only moves points in the xy plane, and the z points are unaffected. Okay, so this is a 3D rotation. Okay, it's the same as the one we wrote before, except with that last row added to it. Now, this is the rotation about the z-axis. We can look at rotations about the x and the y-axis too. And similar to this rotation, we can do a similar thing, which is rotate about the x0 and y0. So I'll write those rotation matrices, but if you want to derive them, the derivation is as same as what I did. I think it was in the first or second class where I derived that expression. So if you want to look at rotations about y and x, they would be of this form. Let's parameterize the rotation about the y-axis with theta. So we would have cosine theta 0, sine theta 0, 1, 0, minus sine theta 0, cosine theta. And Rx, let's parameterize that with phi. That is 1, 0, 0, 0, cosine phi minus sine phi, 0, sine phi, cosine phi. Okay, now I want you to note something, which is if you look at this rotation, you can see there's a negative sign here at row 1, column 2. If you look at Rx, there's a negative sign, looks similar, except it's moved around. But then here, there's a negative sign over there, it looks like that's a mistake on my behalf writing this down, but that's not right. This is the correct way of writing this rotation. So this is not an error. This is how the rotation is. And the reason why this happens is because you have x cross y, z, y cross x is x cross y, z, y cross z is x, and so on. If you look at the cyclic rotation part of it, you will see that that negative should occur at the place where I've drawn it, and that's not an error. Okay, so this is a common mistake people make, is put it the wrong way. That is, they put the negative sign here, but that will give you the transpose of r, which actually corresponds to rotation about the negative theta about the negative y-axis and not positive y-axis, or rotation by negative theta about the positive y-axis. Okay, so I put this down as a rotation matrix, but then when we want to look at something in 3 dimensions, it could be, it doesn't have to be rotated about the x, y, and z. It could be some random rotation about some degrees about x, some degrees about y, some degrees about z. So what we do is we can write a general rotation matrix. That is, this is something which is more generic than what I wrote down here, as R equals R11, R12, R13, R21. So this suggests that there are 9 numbers in the rotation matrix, which means we need 9 things or 9 quantities to define the rotation matrix. But clearly you can specify rotation about just 3 axes. And so there is some redundancy here. And the redundancy is that you don't really need 9 numbers, because these 9 numbers are actually constrained because the rotation matrix has certain properties. So one of the property of the rotation matrix is that if you take the rotation matrix and you multiply it with its transpose, so you could do it this way, you could do it that way, it will give you the identity matrix. 3 by 3 identity matrix. Okay, what that physically means is that a rotation matrix will not cause the vector on which it acts to scale or scale by a quantity. That is, if the length is x units, it will remain x units, it will not increase or decrease. That's one property. The other property of rotation matrix in the specific cases scenarios we're looking at is that we are looking at orthogonal rotations. That is, the x, y, and z axes are at 90 degrees to each other. Okay, and based on those, you can write the following conditions. So one of the condition is that it doesn't scale any vector on which it acts. So if you do this for 1, 2, 3, maybe I should write it. Let me do it this way. It's much clearer if I just write down the expression R11 square plus R21 square plus is equal to 1. So that's taking the first row, sorry, first column, right? To second row, first column, third row, so it's the first column, and then squaring it, it should come out to be 1. If you do this for the second column, you get 1, 2 square plus R 2 square plus R 3 square equals 1. Third column, 1 3 square plus R 2 3 square plus R 3 square equals 1. So that is just saying that rotation matrix has unit magnitude. So if you ensure that each column is squared as 1, that means that it's not going to scale any vector. The other property is that they are orthogonal, which means that you write it down as R. So you take the individual columns and multiply them together. So you can write it as RI1, RI2. Here we can sum over 1. So 1, 2, 3, which means that if you do this, you'll get R11, R12 plus R21, R22, R31, R32. And then similar expressions for the other two columns. RI2, RI3, 1, 2, 3 equals 0. And then RI3, RI1 equals 0, where I will be 1, 2, and 3. We'll follow a similar strategy to expand it out. Okay, so what we have here is 3 conditions for the fact that could scale, and then 3 conditions for rotation matrix, orthogonality of the rotation matrix. Okay, so these are 3 conditions. Okay, so effectively we have, remember, 9 constants, which I wrote down earlier, 9 numbers, but those 9 numbers are related by 6 conditions which you cannot violate, which means effectively there are 3 unique numbers in the rotation matrix. And so you need only 3 things, 3 quantities to, to define a rotation matrix, not 9, which a rotation matrix represents. Okay, so now the way people go about parameterizing rotations is through what are known as Euler angles. So we use Euler angles to parameterize rotations. So what are Euler angles? What we do is we take these rotations, I showed you rotations about X, Y, Z, and we sequence them such that we can represent any rotation of an object. So you take any object and then rotate any way you want, and it ends up in a certain orientation with respect to X, Y, Z. Then Euler angles will tell you that you can decompose those things into 3 numbers. And those 3 numbers are 3 unique rotations about 3 axes. And so the way we choose these is as follows. Euler angles, the set of 3 angles. Okay, so what you can do is you can choose them to be rotation about the x-axis followed by y-axis and then z-axis. So if you do this sequence of rotations, you can represent any rotation. But you can also do it by interchanging z and y. Okay, so it will be that you will represent the same rotation, but it will be different parameters, different angles, because those 2 rotations are sequenced differently, and we'll get to that in a bit. You could also do x, y, x. You can do x, z, x. Okay, note that you cannot do x, 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 because that will not give you rotation, orthogonal rotations. It will all be rotation about 1 axis, it will be planar rotation. So you are not allowed to have 2 consecutive axes to be the same. X, x, y is not allowed, but x, y axis is allowed, because when you go from x to y, you go out of plane and then you come back into the plane x. Then we have y, x, z, y, z, y, y, z, x, y, x, y, z, x, y, zy x, vy z, then z x z. Okay, so we have, so these are all the possible combinations of the three rotations. So we have 3 here, sorry, 4 here, 4 here, and then 4 here. So if you add all of them, you have 12 unique ways of describing rotations. Okay, now when I'm saying unique ways, it means that it's the same thing. If you take an object, you rotate it, you get the same end result. That is, you explain the same object, but it can be done in 12 ways. Think of it like this. If you want to describe a word, say apple, and you want to describe it in 12 languages, there are different names for apple in 12 languages, but it means the same, it's the apple. But then there are 12 ways of saying it. So that way, you will have different words which you say to describe the apple, but they will all be, they will look different when you look at the words, but when you look at the object, it's the same thing, it's an apple. So the object here is the same orientation, but it's described in 12 ways. Now, there are specific ones which are more popular than the other. One of the popular one used is what is known as the 1, 2, 3, which you can see is clearly the X, Y, Z orientation. This is known as the Bryant angles. Okay, so another popular one is Z, Y, X and Z, Y, Z, I think. So we will use this one. Use this. It's also the 3, 2, 1. I don't think it's called, maybe it's called Tate Bryan, I forget. Let me just quickly check. ZXY, that's the Tate Bryan. ZXY. So this not this one, but ZXY. This one has a name. Tate Bryan angles. It's usually used in aerospace. Okay, so now that we have this, let's talk about a few properties. Now, this is kind of important because going from 2D to 3D has its own challenges. Besides, it's more complicated. There's some things you want to know, which you should remember. Rotations in 2D are commutative. Okay, what it means is that if you rotate about θ1 followed by θ2, then and if you interchange the order from θ2 to θ1, then you'll end up with the same angle, right? So same net rotation. So if you start with θ1 and then rotate this vector by another angle θ2, then your net rotation is going to be θ1 plus θ2. Okay, so if you start with θ2 and then rotate by θ1, then you still end up with θ1 plus θ2. So that is commutativity. Okay, which is very obvious from doing this by just drawing a figure. Now, when it comes to rotations, so another way of explaining this is if you do r θ1 and r θ2. So you take the rotation matrix I talked about the z-axis, you multiply the rotation matrices, and then you will end up with θ1 plus θ2. So you can try this out by just doing the calculation. Just use the rotation about z I wrote down earlier. if you do this r theta 2 times r theta 1, you'll end up with r theta 1 plus theta 2. Okay, now rotations in 3D are not commutative. Rotations in 3D are not commutative. Okay, so here's how to illustrate this. We can do this by actually taking a physical object and rotating it. That's one way, but I think I'll just do it on paper. That way, when you read the notes, you'll be able to understand what, with this simple example, that rotations are not commutative. So let's start with an object which has different length, width, height. So we can easily figure out what happens when we rotate it. So the x-axis, let's say here, the y-axis this way, and then z-axis is blue. Okay, so x cross y, when you curl your fingers from x to y, your thumb will give the direction of z, and that's the right-hand system, of course, using the right hand. Now, what we'll do is we'll do two rotations, just two rotations, and we'll change the order of the rotations, and I'll show you that changing the order changes the way this object is oriented after you finish doing those two rotations. So first, let's take this object and rotate it by 90 degrees about x-axis. Okay, so what that means is you will take your right hand, point your thumb along the x-axis and curl your fingers. That will give you the direction which you need to rotate the object. So if you look at it, if you're looking from it this way, because you're always looking from the positive x-axis, you need to curl your fingers of your right hand along this axis, and your thumb is pointing towards the x. So if you do that rotation by 90 degrees, what will happen is, and see if you can convince yourself this is true. This object is going to be rotated. The x-axis will remain unchanged, right? Because you rotate about the x-axis. Since the y-axis is pointing away to the right, it will now rotate by 90 degrees in this direction. So it's going to point upwards. And then z is going to turn by 90 degrees this way. Okay, so it's convincing. You take your right hand, just rotate the object along your 4 fingers of your right hand with your thumb pointing in the x direction. Counterclockwise, right, in the direction shown. I got it backwards. You're seeing from the x-axis. Okay, so okay, let me do it this way. Arrow, okay. I guess so I need to draw it like this. It is, so, okay, the right way to draw it is this way, perhaps. So that shows that it comes, it's outside, it's not inside. So there's a line, and the arrow is above the line and not below the. No. So that arrow is circle, right? It's rotating the whole ZY axis, yes. That's circle. That's circle. Head of the arrow is on the wrong side. I think of it this way. If I look at it from the way I'm looking at it here with my red eye, then Z is up, Y is to the right. And then this is
now, if you rotate it, and you keep the trend of that curve, you keep that arrow remains in the head of the other. So this is a limitation of
the drawing. I see. Okay. Okay, so let's do the second rotation now. So let's rotate about the y-axis, okay, by 90 degrees. Okay, so when we rotate about the y-axis, okay, I'm going to try this again, okay? I'm going to see this and rotate about 90 degrees about y. And so if you do it that way, then you will see that we will have, see, that's the top edge. So y is unchanged. Okay, now let's think of what x and what happens to x and y. So x is going to be this way. And then z is going to be this way. Okay, so this is how we end up if we do two successive rotation about x and y. Let's reverse the order. Let's rotate about the y-axis first, then about the x-axis. So rotate by 90 degrees about the y-axis. So you're looking at it from here. You are rotating now again. Point your thumb along the y-axis and curl your fingers. Okay, so rotate by 90 degrees about y-axis. So what will happen? Y-axis will, the object will remain unchanged about the y-axis, but we will have something like this. Y is unchanged. X is, see, X is going to move down now. And then Z would be this way. Right, so yeah, I'm going to try to do this with an object. I think this is really hard to do it on paper. I'm just doing it because people are on Zoom. But I'll do it. I'll use an object and do it and convince you that this works. Let me first finish it this way. Okay, so then we do 90 degrees about x-axis. So when I say 90 degrees about x-axis, I look at it from the x-axis. I would curl my fingers along this. Okay, and so the end result is I've actually lost track of how I actually got these in my notes, but let me convince you via an actual object. Hold on, let me finish this. Good. So x-axis is unchanged. Y is, z is this way. Y is that way. And so the thing we're after is that these two are not the same. We did the same, we did two rotations, first one about x, second one about y. We did y, then x, and then we ended up with this configuration, which is this one, which is not the same as this one. Okay, I did this for the, let's just do it by just actually using a physical object. Okay, for the perfect object. Okay, so let's start with, so okay, this is my object, and then you can see. So x-axis is this way, y-axis is to the right, and z is upwards. X, y, and z. So x plus y is z. Now I do 9. So here's how we do 90 degrees about x, 90 degrees about y. Let's do 90 degrees about x. X is this. So 90 degrees about x. Okay. Now what will happen is x will remain unchanged, it will be this way, but y would be up and z would be this way. In fact, x, y, z always moves, remains the same as the object rotates. X is always going to be here, y is always going to be here, z is always going to be there. So again, x, y, z, x, rotate 90 degrees, we are here. Now rotate by 90 degrees about the new y-axis. So the new y-axis is this way. We rotate this way. We ended. So you see that, you see del here. I started this way, del was up. Now you see del there. So remember this. It should be this way if rotations commute. Okay, now let's do it the other way. X, y, and z. First rotate about 90 degrees about the y-axis. Y is this way, 90 degrees. Okay. And then 90 degrees about the x-axis. Remember the x-axis is always that way because it moves with the body. And then so we turn by 90 degrees about the x-axis. And so del is now this way. So we started this way and ended up this way with the first set of rotations. But when I changed the order, I ended up this way. So rotations do not commute in 3D. That is this is actually something I think I did. This is really hard to do it, draw these figures. It's much easier to do it with the physical objects. What I did, so x-axis is this way, y-axis is to the right, and z is upwards. X, y, and z. So x plus y is z. Now I do 9. So here's how we do 90 degrees about x, 90 degrees about y. Let's do 90 degrees about x. X is this. So 90 degrees about x. Okay. Now what will happen is x will remain unchanged, it will be this way, but y would be up and z would be this way. In fact, x, y, z always moves, remains the same as the object rotates. X is always going to be here, y is always going to be here, z is always going to be there. So again, x, y, z, x, rotate 90 degrees, we are here. Now rotate by 90 degrees about the new y-axis. So the new y-axis is this way. We rotate this way. We ended. So you see that, you see del here. I started this way, del was up. Now you see they are there. So remember this. It should be this way if rotations commute. Okay, now let's do it the other way. X, Y, and Z. First rotate about 90 degrees about the y-axis. Y is this way, 90 degrees. Okay. And then 90 degrees about the x-axis. Remember the x-axis is always in that way, because it moves with the body. And then so we turn by 90 degrees about the x-axis. And so there is now this way. So we started this way and ended up this way with the first set of rotations. But when I changed the order, I ended up this way. So rotations do not commute. So if you run this, it'll actually do this 2 rotations in that order, and you can then hopefully get a better sense. So this is how the starting position is on the left. First rotate by 90 degrees about the x-axis, then rotate by 90 degrees about the y-axis. This is how you end up with, and you can go home and figure this out slowly, that this is indeed rotation about the x-axis, and this is indeed rotation about the y-axis. The simplest way to check that is to see that the red, which is the x-axis, remains unchanged. So it's rotation about x-axis. And between these two, the green remains unchanged. Green is y-axis, so it's 90 degrees about the y-axis. This undergoes the reverse rotations, 90 degrees about the y, 90 degrees about the x. So here you can see that the white remains unchanged, and then here x, so the the direction remains unchanged. The final configuration here versus here are different, and so rotations don't commute.